Hello again. This is a session to continue the previous recordings about chapter 1. So in this part, we're going to be talking about computer system environments. Okay. So what are those environments? We have a traditional environment, mobile environment, client-server model, peer-to-peer, cloud computing, and real-time embedded systems. The traditional model is basically what we all have at home. So it's basically a standalone general purpose machines. Okay. Of course, they can be interconnected with each other's internet. They talk to each other and they access the web through portals. Okay, we're going to be learning what a portal is in chapter 3. We also have network computers, those kind of traditional models as well. They are thin clients, so basically you have very thin computers this way that work as a client and they are all connected to the internet. And they work, of course, as web terminals. We also have what we call mobile computers, okay? And those computers are connected via wireless networks. And we have, the networking now became a problem because all the resources you have inside your computer are now threatened because they could be, hacked, they could be accessible by any entity outside your domain, and therefore, you need to have what we call firewalls. So even home systems now use firewalls to be protected from any outside attack or intrusion. Okay, now for the mobile, we have handheld smartphones, tablets, and so on. So what is the functional difference between them and a traditional laptop? Of course, a traditional laptop have a higher power of processing, okay, a higher capacity of storage. You can always see those kind of mobile devices to be embedded systems, okay, and the feature of an embedded system is the low capacity of storage and low computational power compared, of course, to regular systems. But it has extra features like GPS as an example. Okay, those would be features inside the mobile devices that you wouldn't see in regular ones. Basically, because regular ones are not expected to, move around. It allows new types of apps like augmented reality. Okay, because of all the capabilities that is being added to the mobile devices nowadays. And of course, it works using cellular data, okay, for connectivity. Okay, the big things, the big leaders of those, the big players are Apple iOS and Google Android. Another model is the client server, and the idea behind the client server is that you would have several computers, regardless what the type is. So you can have a desktop, you can have a laptop, you can have a smartphone, you can have whatever, and those connect to certain server through the internet or a network. The biggest example of this is a student registration system like Moodle as an example. Okay, you basically connect to this server to see all your registrations, all your grades, presence and absence, and so on and so forth. All your information are on this server. You log in to the system via network and retrieve all your information. Peer-to-peer means you have multiple computers like that, and they are connected. So the connection here is direct between every two. If all of them are connected this way, we call it fully connected model. Fully connected model. And in this case, if those connections are bidirectional, then the number of connections you have is n multiplied by n minus 1 divided by 2, where n is the number of computers you have. Let's see. Let's count those. Here is number 1. Here is number 2, 3, 4, 5. You have 6. You have 7. You have 8, 9, and 10. Why do you have 10? You have 5 computers. Okay, so 5 multiplied by 4 divided by 2, which is the 10. If the connection is directed, so you have a directed graph, so in other words, the connection from, let's say, client 1 to client 2 is different from the connection from client 2 to client 1, then the equation becomes n multiplied by n minus 1, and that's it. So the number of connections would be 20 in this case. Okay, if this is direction or directed connection. Okay. So basically, the direction matters. Of course, when we're talking about communication, usually the connection doesn't matter when it's peer-to-peer this way. Okay. All right, so this is what we call peer-to-peer, P2P. Okay. Of course, the P2P, they don't distinguish clients and servers, so there's no difference between clients and servers. They are all the same. Okay. Now there is no boss here, so all the nodes are peers. Okay, so that's why it's called peer-to-peer. Okay. Anyhow, now we have something called another model, cloud computing. And the idea behind cloud computing is having multiple servers on the cloud, and you can buy certain service from this cloud. Okay, so you can buy software access, so you're not going to be installing the software but use it where it is. Big example for this is basically Google Documents. You know, it's free but it's cloud based. Okay, so you don't have the reader of the documents or the creator of the documents installed on your machine. And instead you actually go for Google, you go Google Documents, you can do whatever you want. Okay. So the cloud can be broadly classified to be public cloud, private, and hybrid. The public cloud is a cloud that is available via the internet, of course, to anyone willing to pay. So anyone can be a member of this public cloud. The private cloud, however, it's run by a company, okay, for the company's own use. All right, it could be an actual cloud or a cloud defined inside the company. All right, and the hybrid includes both public and private. So part of it is public and part of it is actually private, that is only for the company members. All right, the services that are being provided by the cloud, okay, you could have SaaS, which is software as a service, software as a service. As I mentioned, you can have something like Google Cloud, you can have an online compiler, you can have a database server, you can have whatever you want on the cloud. You don't need to install it on your own computer. You can also have platform as a service, PaaS, platform as a service. Okay, and this, in this case, you have a platform. So it could be a database server, it could be an operating system, whatever environment that you need. So you buy the environment itself. Okay, and of course you can have an infrastructure, which means that you can have, a space for storage or something. Big example for this is iCloud, okay, for the Apple users, okay, the iCloud. All right, and it looks like that. A big part of it, as you can see, is the virtual machines. You see, here you have virtual machines, you have storage, okay, you have, of course, a cloud manager. Okay, as you can see, you have here a load balancer that balances the load between all those servers. Whatever happens after the load balancer is not visible to you. So you don't know where your stuff are. All you know that you have a domain, you have a space, you have a service that you are a member in, and you are using this. Where it is inside the cloud, you don't know, and you don't care to know. Okay, it's behind the load balancer, and of course it's protected by the firewall. Here, the cloud customer interface, you log into this system and you virtually look at that, but what you actually do is go through the firewall to the load balancer and you get your stuff. Okay. We're going to be talking about the load balancer in much deeper details next chapter. Well, chapter 3, I mean. Real-time embedded systems. Okay. Those are systems that have real-time behavior, and it's very important to know what a real-time behavior is. And a lot of people mix between real-time and being very fast. They're not the same, okay? Real time doesn't really imply being fast. What it does is it means that every task has a deadline. Okay, so let's say this task has to finish between time 30, okay? If it finishes after the time 30, it means it missed the deadline. So what is a real-time system? It's a system that tasks have deadline, and if you miss the deadline, then there is a consequence, okay? What is the consequence? Depends on the system and depends on the nature of the system, because real times can be soft or hard. It's very obvious that soft real-time systems have easier consequences than hard real-time systems. We're going to be talking about this in details later. Okay, now let's talk about the kernel data structure. So the kernel can have what we call singly linked list, which is, as you know, a linked list that is unidirectional from the head all the way to the null or the tail, depending on your implementation. Doubly linked list means every node, here is the head, here is the tail. So every node has a next pointer and a previous pointer. Of course, the head previous is null and the tail next is null, okay? And you have a circular linked list, which means that the tail actually points next. The next of the tail is actually the head. So it acts as if it is circular this way. Okay, we also have, as you can see here, the binary tree. Why do we have binary tree? Look at that. If you have here an array like this, and the array length is 1 million elements. So, and you're looking at something, you're searching for something, your worst case scenario is 1 million searches. All right. What is the worst case here is when what you're looking for is in the last element or it doesn't exist. Okay. However, if you put those data in a different data structure, which is the binary, so by a binary search tree this way, which means that all the left are less than the key and all the right, are higher than the key. So this means that your worst case scenario here is actually 20. See, this is a 1 million, this is 20. So if you actually put 1 million elements inside this tree, and the tree is balanced, it has to be balanced, of course. Okay, then your complexity here, the maximum number of iterations you need to do in order to retrieve your answer is 20. So you actually brought down 1 million to be 20. How is this possible? The complexity of the balanced binary search tree is log n. So log 1 million to the base 2 is actually 19.2, which is maximum of 20. Okay, you can actually try it. Also, we use hash functions. Why? Imagine this scenario. If you have the fastest search algorithm is not really fast enough. So if the fastest search algorithm is not really fast enough, this means that the whole search algorithms are not suitable because the fastest of them is not fast enough. So how can we solve this problem? We can simply convert the search problem to be a problem of calculation. How is this and what does it mean? It means that instead of searching for the element, you actually calculate its index. So you converted the complexity of search from order of, let's say, log n to the base 2 if it's a binary tree, to be order of constant because it's a mathematical calculation. Of course, it's not order of constant. It depends on the bucket length, but in your best cases, you're gonna go for the order of constant. And that's the end of chapter 1, and we're gonna start talking about chapter 3 in the next video. Thank you.